Hello everyone, guys. This is Machu Singla this side. I recently joined Angel One SSD3 and I interviewed at a couple of other companies. And if you follow me on LinkedIn, you would know that I have been sharing my interview experience is over YouTube. And finally, I am bringing up the interview experience of Angel One. So at Angel One, there are generally 4 rounds. There are 2 DSL rounds, then 1 system design round, and then finally you have a hiring manager round. So in first 2 rounds, where the rounds which are DSL rounds, each interview is related to DSL only and nothing else is asked, and you generally face 2 DSL problems in those DSL rounds, and the complexity of those questions is medium to difficult. And in third round, you are being asked system design, where it is mostly focused on high level design, and there are some components of low level design also. And hiring manager round, what I have heard is it depends upon manager to manager, but in my hiring manager round, my previous experience projects were discussed, and my manager went into depth, and based upon the interview discussions, I finally decided to go ahead with Angel One also. And last month I joined Angel One. So let me share the first problem from the first interview, which was asked at Angel One. So this is a problem which was asked during my first round of Angel One DSL round. So let's quickly look at the problem, and then we'll see how to approach it in interview and how I actually solved it during the interview. So the problem statement is, you are given a 0 index array of integer nums of length n. You are initially positioned at the first integer. Each element nums I represent the maximum length of a forward jump from index I. In other words, if you are at nums I, you can jump to any position which you can reach from that, basically using this nums of I, right? This is what is given here, and return the minimum number of jumps to reach nums of basically you need to return the minimum number of jumps that you need to reach the last index of the array, and the test cases are generated such that you can reach the last index, right? So let's take some examples to understand the problem statement further. So this is given an array, and you are initially standing here. So each number in array represents a number of steps that you can take from there. So if you are standing there, so basically you have the power to take 2 steps. So you can either take 1 step or 2 steps. So if you take 1 step, you end up being here. If you take 2 steps, you end up being here. But you cannot reach here, because reaching here needs 3 steps, 1, 2, 3. But you can take at max 2 steps, right? And you need to reach here. And you need to reach here in such a way that you are taking minimum number of jumps. So the way jump is defined, if from this index you are going to this, it is considered 1 jump, and from this, if you're going to this position, it is also considered 1 jump, right? So from in this case, from 0th index, you can either go to first index or second index, right? Both of them will be considered 1 jump, right? Now, if you think like, if I want to minimize the jump, should I go to the farthest one, which I am looking at? So if you jump here, right, from here, how many positions are possible? Basically, here you can use just 1 step, or basically distance of 1 is what you can cover. So you will be able to reach here only, right? So if from 0th index you go to second index, right? So now from second index you can cover in distance of 1 only. So you would reach here at your third index, right? Now from here, again, you can cover a maximum distance of 1 only. So you would reach 4, which is the last index. So here you use total 3 jumps, 1, 2, 3, right? So this is 3 jumps, or basically you can say 3 steps is what you took. And let's consider another way, like from 0th index, if instead of landing on this position, if you had landed upon this one, the first index. So from this you can cover a maximum distance of 3, right? So this distance is measured in the number of indexes where you can reach. If you are here, you can cover a maximum distance of 3, which is basically you can either go here with which is at distance 1, this is at distance 2, or you can reach here which is at distance 3, right? So from 3 you can directly reach 4, right? So if you see how many jumps did you take, so you took 2 jumps in total, right? So this is a better approach than this one, or basically this is more optimal, right? So this is what you need to solve. Let's look at one more example before we proceed. So from this 0th index you can cover a maximum distance of 2, so you can either reach 1 or 2, right? So from 0th you can either reach first index or you can reach second index, right? So if you end up being on second index, so here from here you won't be able to go forward, because if you're standing here the maximum distance that you can cover is 0. So basically it doesn't give you an answer. But from first one, what you can do is you can either reach this index. So if you're standing at 3, which is your first index, you can either go here or here or here, which has distance of 3, right? So if you want to understand like how distance is being calculated that I am talking about here is, so if you are at nums of I, so basically if you are standing at ith index, you can jump to any nums I plus j where j is less than equal to nums of I. Basically you can go forward any number of steps which is less than this current number, right? So from 1, if you are here, you can either go here, here or here, right? So from here you would be able to reach here. So from 1 you can go to 2, so from 2 you know there is nothing, but from 0 to 1, if you go to 3, if you reach here, you can take 1 step from here and you will reach 4th index. So you took a total of 3 jumps, right, in this one. But instead of going to 3rd, if you have gone to this 4th index itself, so this is your destination index, so you would have reached here in just 2 jumps, right? So I think by now you would be getting some idea. What we are trying to find out is the smallest distance between the first index and the last index, right? So whenever things like this come, return the minimum number of jumps to reach nums of or basically to reach some node. So we generally think of BFS. And how does your graph look like if you have to build a graph here? So if we are looking at this example, so if I represent this as the indices, so basically a node by indices, so from 0 you can either go to 1 or 2, and from 1, when you are here, you can either go to 1, 2, 3 or 4, 2, 3 or 4, right? If you are standing at 2, you can go only to 3, and if you're standing at 3, you can go to 4. But when you're standing at 4, you can't go further from here, right? And there is no point in going from the current position to the position itself. So there is no point in adding 1 here itself, right? Because you end up in being same position. So that doesn't help you optimize the cost. So this is how you can build a graph, right? And in this graph, so how do you build this graph? Basically, whenever you are on some index, you iterate through the following indexes based upon what is the value here, and you keep adding those indexes to the graph list or adjacency list for that index, right? That's how you build the graph. And the weight of each edge is considered as 1 jump, right? So all of the edges are of same weight. And now once you have your graph, so all you need to do is you need to reach from node 0 to node 4, and you can apply BFS on this. So you can calculate like how BFS will look like. So what we did here is essentially BFF directly or indirectly, the way you want to say. So coming to this is one approach to solve it, right? But now since you are in interview, you are expected to evaluate the BU analysis also. You are expected to tell the space and the time complexity, right? So talking about time complexity, so when you are using basically a BFS approach, what is the time complexity? It is big of your number of vertices plus number of edges, right? So in this approach, what you are going to do first you build the graph, right? And then you perform BFS, right? So what is the time complexity for building this graph? So the way you look at it is you call it adjacency list, right? Let's say you have n numbers, or the length of your array is n. So for each adjacency list of I, what you do is you run a for loop, right? For basically you can say index equal to I to index equal to I plus nums of I, right? This is what you do. And to adjust the list of this, you keep adding this index, right? You can say +1, right? So what you're doing basically is this is something that you do for each node. For I equal to 0 to I equal to n-1, considering 0 based indexing, this is what you do. So basically for each node you are building the graph, right? So what is the worst case time complexity for this, for building this adjacency list? It is big of n square, right? Because it is a nested loop over n. This is a loop over n, and in worst case, like each index might have a value which is reaching towards n, right? This is for building the adjacency list, right? And now when you perform BFS on this graph, so what is the number of vertices that you have? It is n, because you have this n node, right? And how many edges you can have in worst case? So in worst case, how this array will look like, basically each number is big enough that you can reach till the end of array. So from each index you can reach n index in the right. So worst case adjacency list will look like from 0 you can reach to 3, 4, or basically till n-1 index. Same for 1, right? From 1 index you can reach n index till n-1, right? So again, number of edges in worst case would be of order n square. So that part will be number of, basically this part becomes vertex is n, and then edges become n squared, right? So your time complexity becomes n square in such a case, right? And talking about space, so what space are you using addition here? You are creating a graph using adjacency list, and the worst case again it depends upon the edges you have, and that is n square, right? So worst case is n square. So you would be using some queue or visited array also as part of BFF, but that will be big of n, right? So that would that is something that you can remove, because we have already something bigger than that. So this is the time and space complexity. So this is one approach. Now there is one more optimized approach which interviewer might ask you, like how can you improve in on both time and space. So let me tell you this approach, how to solve with that approach. So you would be able to use this approach in interview, like if you have solved some problems on some competitive programming platforms, or if you have practiced this problem before the interview. So let's look at this. So understand from this 2, when you are adding this 0, you have basically a power, or you can say you can cover a distance of 2 from here, right? So that's where you can land, right? So basically you are running up with this, and so let me write down this array this way, 3 1 1 and 4, right? And when you are here, you are at index 0, and you still have the capability to cover a distance of 2, right? And you can remove this. This is just basically index that we are iterating. So you still have the capability of covering 2 distance, and this is your beginning distance. And now when you are at 3, you still have a capability of covering one more element or one distance from your current capability, right? Because you have used one, you can further use one, right? And now you see, because you are going further, along the way you will keep looking at the numbers that you should be using next, because the problem is basically where you should land next, and you want to land on a vertex such that you can cover maximum distance from that vertex, right? So if you would have picked 3, right, because there is something where you could have reached with your current power, then you would have a power of 3 here, right? See, and now when you are at this index, your current power, which was initially 2, which had become 0, 1 here, so it would become 0 here because you have exhausted all of it. And when you are reaching here, if you would have picked this one, so your new power would have been 1. But if you would have picked this one here, which would have given you power of 3, so this would give you a power of 3 minus 1, because considering you have picked this one, you would have consumed 1 while coming here, right? So the power of 3, or basically the distance that you have covered with 3, it becomes equivalent to 2 when you are comparing it here, right? So now, since your current power is 0, you need to pick a power, right? And you could have picked these 2 powers. So now the way you select which one to pick, you basically see which one is maximum, right? You do not worry which one is the one that you're picking up, but you need to know like what is your current power, right? Because that is something that will decide where you can reach, correct? So you would basically have a maximum effective power that you have current, and you have a current thing that you can pick. So what you say is from 1 and 2, these are your options here, right? When you are standing at this index, so you pick up 2, and now when you come here, so this 2 becomes your current power here, right? And when you come here, your current power becomes 1, right? And now since your power had become 0 on the previous step, so now you would again looking for the next jump or the next one that you should be picking up, right? So now your option is 1 that you have here, and your current power is 1, right? And now when you go to the next position, your current power becomes 0, right? And now you look here, if you would have picked this one, so your effective power would have been 1 minus 1 from there, and it would have become 0, right? And you could have picked 4 from here, but you don't need to pick anything because you have reached your destination, right? So this is how you can basically calculate or basically pick the numbers optimally, and how many jumps you are making is equivalent to this. So you see, so how many jumps are you making on this one? So whenever your power becomes 0, so see, initially your power was 0, and since you were standing on the first num, your power becomes 2, right? So that is not considered a jump because you are starting from here. So your number of jumps become equal to the sum of the times your current power becomes 0. So it is becoming 0 2 times, 0 or here. So basically either you are reaching the last element C, if this would have been 4, right? So effective it would have been 4, right? and this would have been 3, you would have picked 3, right? And this would have become current power would have become 2, here it would have become 1, right? So you keep adding 1 to your jumps whenever your power becomes 0, or basically or you reach the last element, right? So that is how you count the number of jumps. So let me explain with let me quickly briefly explain again here, like how I was doing this thing, if it isn't clear. So see, when you are standing here on 2, let me remove all of this. So 3, 1, 1 and 4. When you are standing here, your power is 2. You go here, so you can still cover a distance of 1. So this is what you tell, your remaining power is 1. And now when you come here, your power becomes 0, current powers become 0, right? So you can't go any further. So this is where you can reach from your current position, right? And now see, so since you could reach here or here, so you could either pick this or this. So now let's say if you would have jumped here on 3, right? So how much distance would you have covered as compared to this? That is the comparison you need, right? So if you would have jumped here, you would have power of 3 here, a capability of covering distance 3 from here. So with 3, this 3 effectively becomes 2 here, right? Because you have already used 1 from going to this index to this, right? And when you are here, you are starting with 1, so your current power becomes 1. So you see, whenever your current power becomes 0, so you pick which is the biggest one, right? So you pick this, which is your 2, and to your jumps you add 1, which was initially 0, right? So if you say that you change your power to 2 from here, so what you do is now your power becomes 1 here, right? And you discard all this. You don't need this because you already picked one of them. Or basically what you can do is all right, just disregard, right? So with power 2 from here, you would have reached here, and your remaining power would have 1. And now your available option is this one for the next jump that you could pick, right? And now when coming to the next element, your current power becomes 0, and effectiveness of this one, which if you have picked from here, would have become 0, right? So in this scenario, you have reached the last index, so you basically end up jumping here. So this is what your number of jumps become, right? So that is how you're calculating. Let's code, and then you will be able to understand more from the code how to do it. And looking at the time complexity, what we are doing is, so we are iterating through the array, and what I am keeping a track of is, I am not keeping a track of all the effectiveness that we have. So if you look here, and there had been a 4 that you have, and let's call it 3, okay, let's call it 5, right? So for this 3, you could have reached here with remaining 2, 1 and 0, right? So this 5, if you are picked here, this would have been 5, here its equivalent would have been 4, here its equivalent would have been 3, right? And if you consider this 3, its equivalent would have been 3, and its equivalent would have been 2 for this position, and if you pick this one, it will be equal to 1, right? So you start from here, you iterate to the next step, and you pick up, you maintain this in only one variable, that what is the next jump, or basically next jump, you call it 5 because 5 is the value. And when you come to next element, what you say is you reduce 1 from your next jump, right? So next jump becomes 4, and then you compare it with this 3, right? If this 3 is more than your next jump, because you just need to maintain one next jump variable, which is the maximum value that is possible from the last index where you are reaching, right? And once you have that value, you just use it. So you don't need to maintain the effectiveness of all of them. So you see that your next jump is still greater than this. So no change right now. And now when you go to this index, again you reduce the next jump by 1 and becomes 3, and then you compare it with 1. So when you are here, this information is closed. You are just left with this next jump was 4 and now it becomes 3. So you are comparing 3 with 1, right? So in terms of time and space, so time and space complexity are really important during the interview, because that is the only metrics how you can compare two of your solution. So coming to time, what you're doing is you are just iterating through the array, right? And you are maintaining 2-3 variables. That's all you're doing. So time complexity becomes big O of n for this, and space complexity is big O of 1. Space complexity becomes big O of 1 because we are just maintaining this number of jumps that we have taken, and what is the next jump, and what is the current power remaining, or basically current distance that you can cover that is remaining, right? These 3 variables, or maybe a 1 or more that we might see during implementation. And let's look at the constraint. So constraint is also like 10 to the power 4 is the array length, and nums of I would be maximum 1000, right? So all right, there's one thing which we need to change here. So I considered n square considering like this value. So let me quickly fix the time complexity and space complexity here. So what you're doing is you're iterating through your array, and the maximum number of iteration would be equal to the nums of I, right? So if you say that m is equal to max of all nums of I, right? So time complexity would have been sorry, this was wrong representation. So it would have been n into m, and for building the adjacency list, and so building the adjacency list would have been yes, and this would also have been n into m, right? So all of these values which I represented wrongly would have been n to m, right? So that is how you compare. Big O of n is much better than this n into m, or basically order of n square, right? So let's code this approach. So what you have here is you have an integers array, right? And let's store it current distances nums of 0 that you can have, right? And jumps initialize at 0, right? And what you do is you start from first index, and you also keep a track of this, like next jump, how much you can make it, call it 0 initially, right? Your I index should be less than nums of length I plus plus. All right, so what you need to do here, right? So first thing you do is you reduce your next jump by 1, right? And you say if nums of I is greater than next jump. So what you basically say is your next jump becomes nums of I, right? And if now what you say is so you store the length also in some variable, nums dot length, right? And you can say if I is equal to n minus 1, or your jumps is equal to 0. So you call it jump plus plus, right? And there's one more thing that you need to do. So this is jump plus plus, and your current jumps becomes your next jump, right? And every time you're coming forward, your current capability reduces by 1, right? Every time you are coming, and towards end you need to return the jumps that you're calculating, right? So let's quickly go through it. So initially you have this power which is being given to you, right? And your initial number of jumps is 0. Your next jump, you can initialize it as 0 because you haven't picked it up yet. Okay, and you also need to make this next jumps at 0 here. Okay, now you have the length. You start from the next index and go till the last, right? And now what you say is you reduce the current capability by 1, and your next jump's power also gets reduced by 1, and you say if current number provides a better range to go ahead than your current effective next jump, then you basically change your current effective next jump. And if you have reached the last index, or you have 0 number of jumps left, so what you do is you call it that okay, you have taken a jump because you're ending over this index, right? And your current distance becomes next jump, so basically you use this next jump thing, and your next jump becomes 0 because you want to initialize it again from the next one, right? And looking at the edge cases, so let's say if you have just one element, so you won't go inside it, and it is the last element itself. Let's do a quick run. So during the interview you should perform a dry run. I'm not performing a dry run because I want to keep the video length short. So you see this solution has given the correct answer for the sample test cases. So looking at the time complexity, what you are doing is this is just one simple for loop, and inside the for loop there are simple big of 1 operation, and in terms of space you are using some constant space only, right? So it's a big of 1 space complexity and big of n time complexity, and if you compare it with space and time here, right, so this solution comes out to be better in terms of both space and time. So let's submit it. Alright, it has given a wrong answer for some case. Let's see. So with this setup you should be getting only 1 jump, right? Let's use this test case here. So if you have 3, 2 and 1, let's see what you get. Your initial jumps is equal to 3, right? Your array is basically 3, 2 and 1. Your current distance becomes 3, right? And this are 0 and this is 3, and you start from 1. Your current distance becomes 2. Okay, so this condition is wrong basically. Yeah, right, I was using the wrong thing. Instead of jump it should have been like current distance, because you should be using the next jump, or basically you should be counting a jump when your current distance becomes 0, right? So let's try to run. I think this would work here. Let me quickly do a dry run here. So this becomes -1, right? And if you see here, so if nums of I is greater than, so next jumps become, what is become? It becomes 2, right? All right. So here it was always considering 1, but now your current distance is in 0 and your I isn't equal to n-1, so it won't go inside. Earlier jumps equal to 0, it was matching. So let's run on this test case quickly. Alright, it's giving 1. Let's try to submit it again. Cool, this solution worked. Cool. So this was the first problem from first DS Algo round of Angel 1. I will share the rest of the 3 problem statements also in upcoming videos. Till then, keep practicing. All the best.